how this perturbation is looking like. It's something periodic, and if the time is changing, then my perturbation is moving. Something like that, okay? That's a running wave, right? So this is my perturbation. And I would like to compute the response of the density. Okay, so if you would be in the Schrödinger picture, right, then basically this perturbation in the Hamiltonian, it would be really like that you will, if you take the acting on psi, and you are in the position representation, then basically this is nothing else as the, in our case it would be that v to the minus, or I have a plus, e q r minus omega t times the wave function at point r. Right? This would be the, in the standard Schrödinger picture, this would be the thing, okay? Schrödinger equation, if I have a potential, basically I multiply the potential at a given point r with r. Okay? I just put a q here because we can solve it for all q at the same time and all omega at the same time. Okay? Great. So what we need to do first, if you remember, I just need to rewrite this term. So what we need to do now, the first step what I need to do is I just need to rewrite the Hamiltonian H pair in the form of some integral, right? Of some operator which depends on the r and some function EHR. Yes, Danny. Huh? Yes, it's a perturbation Hamiltonian. Yes. It's exactly this one. Top one. Yes, yes, yes. Perturbation. Right. Yeah, I'm just repeating that how it acts on the wave function in the X representation that you know. But we need to write it in that form, in the abstract form. Yeah. This, like this is a generic operator. And this is the function. Okay? And I will just write the result and we will see that it's that. Okay? So let's go together. So I'm writing it. And this is maybe the most non-trivial part of that. So as an operator, even I don't need to write it like that. We can do it together. I can write it directly like this. Okay, and here I am writing it as a to the EQR. Okay. This is the operator O at point R, and this is my function H R. Do you see it? We will soon see it, okay? If you don't see it, that we will exactly see it. And as I said, what we are doing always, we are adding here delta t, yeah? So we always can add this, because this will help us to make some tricks if necessary. We can always add this small term to this function. So I'm adding it, but this is the function and this is the operator. Do you see that this is exactly this operator? This is the abstract one. So let's check it. So let's take an act at point, I don't know, R0. On this perturbation Hamiltonian, acting on a wave function psi. If I'm plugging here, this thinks whether I will get that thing. That's the point, right? I need to check that this is the thing. Okay? If I'm plugging here, what I'm claiming, then I will get this, which we know from the Schrödinger picture that should be the case. Let's quickly check it. Okay, but it's purely easy, right? Because this is this d-dimensional integral in principle. And then I am having like R0 meeting R, okay? Then I am having here R. This R is meeting the wave function psi, and then I am having some function which is this VQ to the E QR minus E omega t plus, okay, this delta t I added by hand. Do you see it? Give me some signals always, okay? I need the signals. Without signals, I am lost. Great. So this is easy, right? Because we are working in this position representation, this is nothing else as a delta function, right? This is nothing else as the function psi, right? And this is some other function of r. Okay. So the integral is pretty easy because this is a delta function. So we immediately get as a result of the integration that it is the vq e to the e qr0 minus e omega t. Okay, I have also this convergence factor here now added because I added it by hand. There's the wave function at point r0, which is exactly what is here if I will put here r0. We got it. Great. Super good. So we know what is the perturbation, and we see this is the perturbation Hamiltonian. Okay, so it's these operators times some function, and this is this function. Super good. So we have the operation. And now what will be the perturbation? So this was the perturbation, and now I want to compute how the density is changing. So what I would like to do is I apply this system, and then now what will happen? And as I want to draw here, that chalk, what I want to draw here, that I am applying the perturbation. Okay. Before I apply the perturbation, let's say the electron density was constant in space. It was the electron density was a constant in space. Yeah, this we were proving it. That absolute value of psi square is 1 over v, which is a constant, right? And now we are applying the perturbation, and we are saying, like, if you apply the perturbation, then electron will try to somehow accommodate to this perturbation, right? When the potential energy is high, the electrons would like them to stay. However, when the potential energy is small, the electrons would like to go, right? So we are expecting that the electron potential is changing the distribution of electrons, and the electrons would like to be in the position when we are having the minimum of the potential or something like that, right? If there is a potential energy and the electrons say, oh, I can go somewhere when there is no potential energy, I will go there because it's energetically better for me, right? So we would like to compute how this thing is changing due to perturbation, and how the electrons are changing in the space. Did you get it? And you can directly measure it by STM. You can measure the local density of states. So measuring the local density of states, you are able to get something about the perturbing potential. Okay? So the observable R, which we will compute, is the density operator. And the density operator is this thing. And let's say I want to compute the density operator at point R0, and then it would be like that. Is this clear that it's a density operator? Sure, it's clear, because if you take R, psi, psi, what you are getting is it's C R0, R0, C, which is nothing else as a C at point R0, and this is a C star at point R0, which is exactly the density of the electrons at point R. So this is the corresponding operator written in the abstract form. Okay? Is it clear? Perfect. So what I'm going to compute now is the susceptibility that my operator A is density operator, and my perturbation operator O is also a density operator. Okay? And we see what this describes us. This tells us how the electrons respond to the perturbation. Good. Can I go on? Also, you take a photo of me? Fine, may I go on? So I clarify what is my perturbation and what is my operator I want to compute, and I explain the motivation what we can get out of that. Okay, great. So now we just use everything what we'll learn, all the formulas or many formulas, what we'll learn, and we're going to calculate, okay? So I will now erase the blackboard, okay? Okay, so I'm apologizing, I'm writing so big letters, but good. Good. So, when we start, as we said, so what I want to compute is that I want to compute the change in the density of electrons at point R0 at time t0. And we know the result is, okay, this should be the integral over the space, integral over the time. Okay, I can go from minus infinity to 10 times 0, or I can put the theta function there, does not matter. And what we need to compute is this density, susceptibility, R0 minus R and T0 minus tau. And then we are having this perturbing function H tilde, R tau, and in our case this function was given explicit form. It was V to the power of Q. V as a function of Q, and there was A to the E, QR minus E omega tau, and then we added this delta tau. So this is the form of this function, right? I hope I didn't forget anything. Great. So this we want to compute. We really would like to have the formula for that, so we really need to even perform this integral later. Okay, but the first thing to compute this thing, so the first thing on the way is we need to compute the density susceptibility. And we get a formula for that, yeah? So assume our system is homogeneous. I consider electron in box. T minus, tau 0 minus tau. Okay, and we know how to compute it because we derived formula for that. And this was the formula which we derived. There was this Lemon representation, right? So it is a minus E divided by H. Then there was a theta function. T0 minus tau, and then we are getting, there was the general formula, sum over n, sum over m, a to the minus beta n, minus a to the minus beta n. Then we had the z, which was the partition function, and then we had a to the e divided by h bar, an minus am T0 minus tau, and then we had these matrix elements n, and we are having the density operator at point R0, m, and now we are having, luckily, also the density operator, but now at the point R. Okay, fine? This formula we had derived before, right? Even we make a Fourier transform of it later, okay? So I'm now going to calculate this. So I see, okay, to calculate this, I need to know this. To know this, I need to know this, okay? So we are again degrading the problem for the simple problem. So now what is unknown, we need to compute these things. Great. Okay, so we are going to compute it. And for the sake of simplicity, I will just define these things. So I will just, for the next, just to make the simplification in the notation, I will denote these by Pn, and Pm I will define these probabilities. That is basically a to the minus beta n divided by the partition function a to the minus beta n divided by partition function is basically just the probability that the state n is occupied. Yeah, from statistical physics, this is the probability factor. Yeah, by what probability the state with the energy n is occupied. Yeah, it's here. Okay, just to don't keep many things with me, I will just put it like that. Okay, fine, guys, are you fine? Can I go on? Super good. So now we solve the so n and m. Just keep it n and m. Or maybe I can make advertisement. N and m are this, you know, candies, right, or something for kids. So I could bring one NMN and you can say that I was making advertisement and maybe they can pay me some money. That like that. And the energies, we also need to know N and M. Okay, but we did it. So we know that the state N is basically 1 over square root of the volume, add to the some EKNR, right? And the energies we also know, but I don't know use it explicitly, but it is H bar Kn squared divided by 2n, right? If the electrons are having a spin, then I should also have a spin variable here in principle. So there will be some spinor here. But the things I am considering just ordinary Hamiltonian. So my Hamiltonian H0 is spin independent. So basically summation over NMN, I don't need to take care about the spin. The information about the spin I will put into the game if I will put here a factor of 2. Because my Hamiltonian is not spin dependent, okay? And I just can consider on the orbital part. So then if I do this trick with 2, I don't need to care about the spins. Because care about the spin was just done by putting factor of 2. Is that clear? Super good. Oh, you are so clever, guys. So now let's calculate these guys because we need those guys. But it's very easy, right? Because the operator n, R0 in the Schrödinger picture is just nothing else like this. Right? And the operator NR is the same thing. So we just need to compute this. So if I'm now computing n operator, just be careful. Sometimes I am using the same letter and they're having different meaning. So here n is the eigenstate and here n is the operator, yeah? This very times happens in physics and also everywhere that we are out of the letters. Okay, you in Chinese you have enough letters, but in Latin we have just, I don't know, 26 or I don't know, maximum. Okay, so just be careful, the meaning of the letters is sometimes different, okay? Great. So if I'm just calculating, it's just very easy, it's 1 over v. Yeah, and then I'm having these exponential factors. So what I'm getting here is a to the minus EKNR plus EKMR, right? And since I'm computing at the point R0, sorry, then there is R0 and R0. You see, calculation so simple. Do you see it? Guys, also you see in the back? Great. Are you with me? Is someone lost? I need a signal, guys. You are lost or not lost? Not lost. Very good. So at least one is not lost. So I can continue. So the result is 1 over volume. And then what we get is a to the E R, and there was a Km minus Km. Okay? So this guy is done. Super good. And this guy will be also easy done, yeah? Only we are changing the role of M and N. So the other guy is also done immediately. So if I'm computing M, N at point R, N, then basically the result is immediate, and I can just write it here. It's a volume, right? I'm using this calligraphic V because I have in perturbation this non-calligraphic V, yeah? Just to really don't mix things, okay? I just for the volume I am using this V, and then we are getting R0, and there will be a to the E R, and I need to change the role of Kn and minus Kn. Okie doke, fine. Can I go on? Super good. So now we are done. We have those things. Okay. We have all those things. Great. And now we need to plug it back to the formula. So maybe I can just summarize it. So what we derive here is that this is equal to minus 2 E divided by h bar, theta function, E0 minus tau. And then what we got here is, there is the summation over NMN, which is the summation over, since NMN are the quantum numbers, so it is over Kn and Km, actually, right? And then I denoted these things by these probabilities. Super good. And now I have all the time dependence. So the time dependence is here, EH, and I have the energy N minus energy M. Okay, this I'm going to 0 minus tau. Great. And now I'm plugging these things which I derived. So it's 1 over volume, another over volume, right? And what I can write it is A to the, and I hope I will not make a mistake, but I can write it, for example, in the form that it is E R minus R0, Kn minus Km. And here is the square. Now let me check. Yeah, I think it was that. Okay, doc? Very good. Okay, so now we have it. So the calculation now returns to that point. So we now need to take this guy and we need to plug it here and make the integration over time and over the R. Okay? Good. So I will try to calculate here. Okay? So I'm erasing this part. Can I do it? Perfect. So then let's do it. Great. Okay, I can also erase this we don't need, so let me also do like this. Okay, this I'm also dealing that we are having the time, space. Okay, so now I'm going to calculate here. So now I'm writing it here. So calculation corresponds here. So I'm now really computing the change in the energy. Yes, so now this line is continuing here. Good. So basically I need to write everything once more together and then do the things slowly. So then let's do it. And I will change already I am changing so I'm plugging this here and I'm changing the order of the summation and integration. Okay, so you will see what I'm doing here. Just remind you, so I'm getting it 2. Okay, this is this 2 which was there. Then I have this minus E divided by H. Fantastic, I have it. And now I am having this, question? No. Okay, and now I am changing the summation with the integration. So I put N and M or Kn out. Great. Then I have these probability factors. Pn minus Pm, right? This does not depend on anything in R or T. And now I'm gonna to write the integrals, and I'm now having the integral over the space, integral over the time. Okay. Great. And I am plugging the things there together. So I am getting all the time dependence is here. So the time dependence is here. Time dependence is here. And there is a space dependence. So let me write it. So as a time dependence, I am getting A to the E divided by H. Then I am having N minus AM. E0 minus tau. Great. T0 minus tau. Great. Okay. Now I put here to the T0. Okay. Just to keep it to the T0. Then I have this trick with delta function, delta tau. Remember delta minus T0 minus tau. And then I can write this to the delta here. You remember, I was showing you the trick with the convergence factor that I am putting something here, right? And then I need to take it out here. As I'm doing here. Put it in more. Okay, and then we are having this minus E omega T0 I have it differently. Okay, there was this minus tau, okay, from the perturbation, because our perturbation is tau dependent, right? So this is this integral, okay? But what I'm doing here is I'm again making the things simple or complicated. I'm putting minus tau here and also taking it out. So I can write it as a minus E omega tau 0. So this I can put out. Okay, this thing is here because I put it back to the integral, right? Is that clear? Okay, and now I have the space integral, and this is this potential Q divided by volume square. And now I have these two exponentials. And this is a to the e, and now I wrote them here, Kn minus Kn r plus, I wrote it separately, a to the e, and then I have Kn, sorry, this is r0, and then I have Kn minus Km plus q and r, because I adopted this term there. Okay. This term I adopted here. Put it here. Right, and this is what we had before. Is that fine? You see it? Good. So we need now make two integrals. Great. So let's start with the integral over t. So now I can erase this part. Okay, can I just write it? So I will continue here. I can also erase that. Let me write the results. So this is a 2 minus e over h. There are those exponents which I plug there. So delta tau 0 minus e omega tau 0. Fantastic. The summation survive. Kn is surviving. So I'm having these projectors or probabilities. Km, and now I need to make the integrations. Great. So which integration you want to do first? You see how democratic I am? So you can choose. Huh? Time dependence. Fantastic. Time dependence is very easy. So because I can make the change of the variables, I can define the new variable tau tilde, right? So I can define this as a tau tilde. Tau tilde. There is the minus tau tilde, and I can change the integral. So basically, if I'm making the change of the variables, the integral over the time is very easy, and I will just write the result, because what we are getting is the integral from minus infinity to 0, the tau tilde, and I will get this is the exponent, and here I am having minus e omega plus delta minus e divided by h bar and minus am tau tilde, right? If I am just changing the variable. This is going from minus infinity to 0, so tau tilde is just going from minus infinity to 0. Okay? Great. And this integral is very easy, because if I have the integral over alpha x, integral over x, this is a alpha x divided by alpha, right? Okay, this is definite integrals, so it's going from minus infinity to 0, so I need to compute it from minus infinity to 0, so it means it is a alpha to the 0, which is 1, divided by alpha, minus a to the alpha at minus infinity times divided by alpha, right? Right, guys? You see it? So alpha is this thing. Okay? Thanks to this convergence factor, this thing is 0. Right? So what I'm getting is just that out of this integral I'm getting the result, and the result is, did you get this point what I was doing? You today come home and say, Mommy, Daddy, I will show you one trick, and we will show them. Okay. Make the video and you show me, okay? It's a part of the homework. So show how you teach your parents to do the integral with the convergence factor. But you see, in this example, you see why this delta is important. Yeah? Otherwise, we are in SACS, we are getting something at minus infinity which is not defined, right? So, but this delta is doing the job that, okay, things we kill, right? Okay, so I'm getting the result and it is minus, so alpha. So it is minus omega plus delta minus E divided by H, En minus En, and this is just 1. Okay, so integral over time is done. Okay, so I can write it here. 1 over, and once more I'm repeating. Guta, right? Super good. And you even see what will happen, that this thing, if I will take this thing, this thing, and I will put it here, then I can remove this imaginary I and put the H bar there, and I can a little, oh, and sorry, and this is 1 over H. Sorry, minus E, and I forgot, this is minus E over H, sorry. Yeah, this thing it should be there. Right? You see it? Danny? Fine. And I can put even this thing inside, and I can just do it now. I am doing it. You have it before, you took the photo. So 2 will survive, and if I will massage the other things inside, then the denominator will get much simpler. And it would be just H bar omega plus En minus Em plus E delta. Since delta is infinitesimal small, H bar times delta is also infinitesimal small, so I'm using the same delta here, okay? But it should be here H times delta. Because I put something in, right? From this fraction. Okay? Great. Can I go on? Now remains the integral over the space. But what is the integral over the space? If I'm integrating over R, only integral over the space is here. So if I'm integrating over R, I'm just getting nothing else. The integral over that is the volume times delta function Kn minus Km plus Q and 0. Because I'm having the plane waves. Right, this is the integral, is just the delta, no delta function, Kronecker delta. If this thing is equal to 0, then I am integrating number 1 over the volume, so I'm getting the volume. If this is not a 0, then this is 0. Right? So, if I'm using these results for the integral over the volume, then what will happen here? I am having here volume, delta function, Kn minus Km plus Q, and then I am having this factor, the Q divided by volume, and then I am having this thing, this remains, a to the E Km minus Kn R0. Guys, I am doing some magic and you don't understand? Because out of your faces I am reading some. Is it clear, Danny, or not? Chepin? Okay, guys, I don't know other names, so I just know 3 guys in the audience. So I don't know how I should call you. It would be maybe better if you can tell me your your names and then, because I like to call the guys by names.
The changing variable, how
Yes,
minus,
yes. And
I mean the sign, minus.
this should be minus, yes. Yes, Danny, it should be minus. Then you have the minus here, but you also change the boundaries, yeah. Okay? Good. Fantastic. What remains is to make one last summation, but it's very easy, because what we can do is, we can, let's say, express the Km, because this is a delta function, so this thing is non-zero only in the case when momentum Km is equal to Kn plus Q. Right? And then I can make the one summation for free from this summation, right? Because this I can sum over the Kronecker delta. So I'm now writing the final expression. So I'm continuing here, and the final expression is here. So if I'm collecting all the terms, then the final expression is here, that it is a to the delta tau 0. Okay, this is this guy. Good. And then I have 2 divided by volume. So 2 is from here, right? And one volume here is canceling the other volume. So only one volume survive. Okay? Good? And now I'm going to write what remains is the summation over Kn. And what I am having here is this probability factor of n minus probability factor of, or I can write it Kn, and the probability of Kn plus Q. Yeah, this comes from these things, because Km should be equal to Kn minus Q. Then I am getting the denominator. Oh, let me write it in the denominator. Sorry. So P Kn minus P at Kn plus Q. And then I have a denominator, h bar omega plus energy at Kn minus energy at Kn plus Q plus E h bar delta, but I'm not putting delta there because we sum it to 0 at the end. It does not matter. Okay? And then what remains here is just this thing. VQ and this thing. And this is VQ. And this is A to the E. And because Kn minus Km is equal to minus Q, basically I can also express these things together, and I will get that this is nothing else as the A to the EQ R0, right? And I still have this thing, and I'm putting it back, so it's minus E omega to 0. Done, yes? I delta. Because we have this expression here after integration. So before we have this minus E over H, right? And then I have in the denominator something like E omega something. I don't remember. There was a. Yes. I'm just saying that I can also write it here if you want, but this does not matter because at the end delta is going to 0. If you want, I can write it like that. All right. But many people are not writing it because it's always at the end delta you take it to 0. So you don't. But if you want, then it should be like that. Apart of that, everything clear? Guys, is it? Do you see it, what I did? Do you understand each step? It's fully important. Great. So we derived something, what we will see later, and this function has a very special name. not this, but other function which involve this function, but I will write it also here. This is called the Lindhardt function. So basically, what we see, just guys, what we see that the change in the density is proportional to some function which characterize the free electron gas, because this is the energy of the free electron gas, this is the probabilities of the free electron gas. So all the properties of the unperturbed systems are hidden C. Here you see there are just properties of the unperturbed system. H0. All properties of this system are hidden in this thing, right? And then we are getting the same perturbation here. And that was the perturbation here, was this. And we are getting the perturbation here. So we see that the electron gas is in the phase, is coherently changing with the potential. Yeah, if my potential is varying with Q and omega as a standing wave, then also my electrons are responding to that as a standing wave, right? So its response is in the phase. Do you see it? That I apply the perturbation which is time dependent and position dependent as a wave, and I am getting also the response of the electrons going with the same group velocity and the same thing, right? Now if I would have a general potential, like I computed here for the very special perturbation. I choose very special perturbation and I get a very special answer. But this is the, okay, once more refining. So this is the, this depends on only depends on H0 and temperature, like equilibrium properties of the unperturbed system. I just need to know eigenenergies, probabilities, factors, and I should be able to compute this sum. And I will get some object. And this is called the polarization function of the electron gas. How the electrons are getting polarized if you apply the external perturbation. Okay? Okay? Or not? What's not clear? You need to write what I'm saying, or what's not clear? Then you go on. But which part? Okay, I will. Let me clean the blackboard. Can you formulate your question during I am cleaning the blackboard? So, okay, out of this calculation, what we get? Once more, what we get? We get the change of the electron density at point R0, T0 is proportional to such function. Sometimes this function is called like P0, or sometimes this function is called also chi0. And we get that there is this perturbation VQ A to the E QR minus omega t. So what this quantity tells me? Before the perturbation, I had a constant electron density in my system, right? During the perturbation, my electrons are doing something. They are changing. And the difference between those two things, which I'm just plotting, because delta n, so this is on n0, this is n due to the perturbation, and now I am making a delta n, which is the difference in the electron concentration with and without the perturbation. and I'm seeing that it's some function, and this function has the same periodicity in space and time as the perturbation has. Right? This is the claim. So electron gas is responding in the same way as the perturbation is acting on the system, okay? There is no the delay, or you generate another frequency or something like that. That you act with the frequency omega and you're getting 2 omega response. This you can get in the experiments, but there are other effects responsible for that. But in the linear response, the electron responds immediately with the same things how you perturb it, okay? So we see it from this, the exponential factor is the same as the exponential factor of the perturbation, right? And the properties of the system are in this function here, which I sometimes call, in some books you will find it, they call it P0, sometimes they call it chi0, but this function is the density susceptibility of the electron gas. Yeah, density susceptibility, this is this function. Okay? Great, what I want to say. So, okay, still 2 comments. Comment number 1. We even can integrate that, and you will have it in the homework sheet, because normally the summation over Kn, you are making the continuum limit, so you substitute d with the volume divided by 2p to the dimension d, and you go to the integral over d decay. Yeah, this is the continuum approximation. I formulated everything for the particle in the box, but if you would like to make the continuum limit, this is the prescription how to do it, right? You know it from the constant matter physics. That summation over the discrete vectors, if you are lowering or making the system larger and larger, or the lattice spacing smaller and smaller, we can compute like that. So practically, if you really evaluate this integral, you will really need to turn it to the integral over case and do it. Okay? Comment number 1. Comment number 2. Why this function is so important? I calculated for a very special perturbation, which is periodic in space and time, harmonic perturbation. But if I would have a general perturbation of that type, I can always write it as some Fourier transform of such things. Right? So in principle, I can write this as a Fourier transform of such things. So for the general perturbation, if what I would need to do would be, I would then need to make the integral over that. So I decompose my perturbation to harmonic perturbations. For each harmonic perturbation, I know the answer, and then I will integrate it back. Okay? So once you know this, you can also compute it for a generic perturbation of this form. You will just make the Fourier transform, use the formula, and transform it back. Okay? Which again brings some shitty integral at some stage, but in principle we are able to do it. Okay? So in the homework sheet, you would be asked to make this thing for particular case that we will consider the electron gas in 1 dimensions. Okay, we will be in the 1 dimensions, and I will give you in the sheet. You will see that I will consider 2 cases. So we will be in 1D. Okay, this will be first case. And we will consider that the electronic dispersion as A depends on the K, because this is just the electronic dispersion, how the energy depends on the quantum number K, right? This is the dispersion. So we will consider the case of the parabolic dispersion, but also you can consider, and you will consider the case of the linear dispersion, okay? This means to make this trick and make the integral. You need to do some integration, okay? This will be the homework. All the time, so far, I was making the averages in the canonical ensemble. I am just making a comment. It would be good if you write it. You can also do it in the grand canonical ensemble. Nothing would change, only this probabilities factor will be different. Because all the statistics was in these Boltzmann factors and 1 over z things. So if you change that, also this will change. So if you will do it in the grand canonical ensemble, this will change. And for the electrons, you will get the Fermi-Dirac distribution of the occupation of the energy state Kn minus Fermi-Dirac distribution of the occupation of the state K n plus Q. Okay, this will be the change. Changing of the statistic is just changing the probability factors, but the guts are changing unchanged, okay? Okay? So for example, if you will calculate it for the electron gas, since it's electron and normally electron gas is considered with a given chemical potential, then you should consider the Fermi-Dirac distributions. Of course, for arbitrary temperature, you are not able to calculate this integral because it's very difficult. But in the case that we will, and this will be the homework case, we will consider t equal to 0. We know how the Fermi-Dirac distribution looks like because Fermi-Dirac distribution is just a step function in the momentum space, right? So these things you will need to do in the homework sheet. Okay, now we are having break 10 minutes. If you have questions, we can go with the questions, but if not, then there is a break. So if you have a question, then go on and ask.
So the point here is if we apply the harmonic related, the response of the changing electron density
It's also harmonic.
is also harmonic and with the same phase
Yes, and with the same phase, right?
simultaneously.
Yes.
And for the perturbation, which is not the harmonic, and we do the transform, Fourier transform, we get the harmonic part, and we get when we use this formula to get the solution.
Right.
Okay.
Yes. Maybe I can then PTS. You're right. Basically, what I can call this, yeah, okay.